Talking about motion graphs then, there are two kinds of motion graph that we need to know about here. We have displacement or distance. I'm going to use those two words interchangeably. They do mean something a bit different. I will use displacement throughout here, but if you haven't come across the word displacement, think about it as distance, and we'll look at the difference between the two in a later lesson. So displacement or distance time graphs and velocity or speed time graphs. Again, there's a difference between velocity and speed, but mostly for these graphs, they're interchangeable in terms of you could label the axis one or the other and it wouldn't change the meaning of the graph. Sometimes it does, but most of the time it doesn't make a difference. Now, when we plot these two graphs, or when we have one of these two graphs, there are some things that we can find out. With any graph, we can read numbers off the graph. We can look on a displacement time graph and say after 10 seconds this thing has moved so many meters or whatever. On the velocity time graph, we can say the velocity at 5 seconds was 2 meters per second or whatever by just reading it off the graph. But we can do more than that. We can work things out from these graphs. From a displacement time graph, we can work out the velocity. From a velocity time graph, we can work out the acceleration and we can work out the displacement. And I'll show you how to do those things as we go through here. So that's a summary of what we're looking at. Let's now look at the graphs. So here I have a straight line, and at the moment we don't know what kind of graph this is. So let's say it is a displacement time graph. Let's get some squares behind it to help us read what's going on, and let's get some numbers on the axes. So here we have a displacement time graph. My numbers run from 0 to 60 meters, and every little square represents 1 meter. And I'm going from 0 to 70 seconds, and every little square represents 1 second. So, looking at this graph then, we can say that the distance or displacement is increasing at a constant rate. That is to say, after 10 seconds, we've travelled 4 meters. After 20 seconds, we've travelled 8 meters. So that's 4 meters in the first 10 seconds and 4 meters in the second 10 seconds. And here we're at 12 meters. So there's 4 meters in the third 10 seconds. So every 10 seconds it's travelling 4 meters, or is travelling a tenth of that in 1 second, 0.4 meters every second, 0.4 meters per second. Now what I'm doing there, of course, is what I'm saying is I have gone this far. Let's say I've gone 24 meters in 60 seconds. So that's 24, that's 60. The gradient of that line, which is the change in y over the change in x, in this case being the change in displacement divided by the change in time. The gradient of my displacement time graph is my velocity. Let's look at a different graph then. Here you can see this graph is steeper, and you can see that in 10 seconds we've travelled about 8.5 meters. In 20 seconds we've travelled 17 meters. 30 seconds about 25.5, and so on. So here we've got about 7.5 meters per second. The gradient of that graph would be about 7.5. And then finally, for the straight line graphs, let's look at this one. And you can see here in 10 seconds we've travelled nearly 13 metres. In 20 we've travelled about 25.5 metres. In 30 we've travelled about 38 metres. So again, you can see that regular change in displacement every second. So these straight line graphs, for a displacement time graph, these straight lines tell us we have a constant velocity. The steeper the line, the bigger the velocity. So that's what our displacement time graph tells us. That the gradient of a displacement time graph is the velocity. So that's the first important thing for us to have in our minds. Get that fitting into my screen again. Okay, and let's take that out of the way. So let's then look at not a displacement time graph, but a velocity time graph. So let's make these velocity time. So up the side here, I've got velocity in meters per second, haven't changed my numbers, and time as I had before. Now, my same three straight line graphs. The gradient here is increasing from blue to green to black. And if we look, in 10 seconds, we've covered 4. We're at 4 meters per second. We've gone from 0 to 4 meters per second in 10 seconds. We've gone from 0 to 8 meters per second in 20 seconds. We've gone from 0 to 12 meters per second in 30 seconds. So what we have here is a constant rate of change, in this case increase, a constant rate of increase of the velocity. And you can see with my green graph that constant rate of increase of the velocity is bigger, and with the black graph it's bigger again. Now all the numbers are the same as with the displacement time graph, so we don't need to worry about working them out again, but the point is the gradient of the velocity time graph is the rate of change of the velocity. That's the acceleration. It is the change in velocity divided by the time for the change. That is the acceleration. So the gradient of your velocity time graph, that is the acceleration. So there it is. So we have talked about two kinds of graph: displacement or distance against time, and velocity or speed against time. We have talked about what the gradients of those two graphs mean. With the displacement time graph, the gradient, the steepness of that graph, is the velocity or the speed. With a velocity time graph, the gradient is the acceleration. So that's all very well, but what if we don't have a straight line? What if we have a curve? So let's look at a curve. So if this was, let's make it a displacement time graph again, we can see that our displacement if we take our green graph, is increasing, but the rate of increase is getting smaller, and then it's leveling out up here. So we said that the gradient of the displacement time graph is the velocity. The gradient is getting less, so the velocity is getting less. With this one, the blue one, you can see it's getting steeper. And so, because the gradient's getting greater up here, the velocity is getting greater. How do we calculate the velocity from a displacement time graph that is a curve? Well, the answer is that we take tangents to the curve. So I've pre-drawn here a couple of tangents, one to the green curve and one to the blue curve. The thing with the tangent is that it has to just touch the curve at the point that you're interested in. So here and here. And you make it as long as you can to reduce the errors in the measurements you're going to make to work out the gradient of this tangent. So what you do then is you look at the change in the y value, in this case displacement, divided by the change in the x value, in this case time, and you work out the gradient of the tangent, which in this case would be the velocity. And again here, the gradient would be the velocity. Of course, if we had the same kind of graph, but rather than having displacement, we had velocity. Now the gradient of the tangent is the rate of change of the velocity, it is the acceleration. So it's really important before you start doing any analysis that you look to see what kind of graph you've got. So we know there are two kinds of graph, displacement or distance time and velocity or speed time. We know what the straight line versions of these graphs mean. The gradient of our displacement time graph is our velocity. The gradient of our velocity time graph is our acceleration. And we know how to deal with curved graphs. If we want to know in this case, the acceleration at 35 seconds, we draw a tangent to the curve at 35 seconds, make the tangent as long as possible, and work out the gradient like this. The change in the velocity is the vertical, the change in the time is the horizontal. Divide the change in velocity by the change in time to get the acceleration. So I said we could work out the velocity from a displacement time graph, the acceleration from a velocity time graph. I also said that we could work out the distance traveled from a velocity time graph. So if we look then at a straight line velocity time graph, let's take that one, and let's take our curves away and our tangents away and our gradients of the tangents away. If we want to know how far our object, whatever it might be, has gone in a certain length of time, let's say in 60 seconds, we want to know how far it's gone. Well, if we work out the area under the graph here, this area is the distance travelled, or the displacement. This area, of course, is a velocity times a time. If you remember from your formula, velocity is distance divided by time. So distance would be velocity times time. So here, in this case, we have 60 seconds. And the velocity after 60 seconds is 24 meters per second. So we've got 1,440 meters. So the area under a velocity time graph gives you the displacement.